Why don't we start out with a little bit of review of last time since it's been a little while. So Sheila, why don't you tell us what frequency encoding is all about?
I don't even remember, Dr. Cruz. Oh, let me think.
Joe with Dr. Miller's office, please call 5221.
I think for frequency encoding, you're trying to determine which direction you're trying to code for where the signal is in the patient. So I think for frequency encoding, if I remember, it was anterior to any direction. So I don't really remember. I think I need a refresher. I don't remember.
Okay. Well, let's. Yeah, but they all depend upon the direction of the gradient coils. Okay. So let's go back. Do you remember the analogy that we made last time about a harp? If you put a ROM out in the hallway and you had a harp in here, and you're plucking the strings of the harp, and a ROM could hear the pitch of the string, then since he has perfect pitch and is a great harpist, he could tell you exactly which string you plucked by just listening to the note. Right? What the hell was that? Do you remember that? So, and the pitch of the string is just the frequency of the note that's played. So therefore, if you take a harp like you see in the center of this picture, you basically encoding the direction along the harp by using frequency. If I pluck a string here, it's going to be a low frequency, and you know it's close to the person who's playing it. If you pluck one way out here, it's a high frequency, and you know that's very far out. Does that help your memory any? So how do we do this with MR? Rob?
I mean, I'm not sure, but somehow by setting up the gradients and, the molecules resonating at different, frequencies along that gradient, somehow you could transform and compute where you are in space based on that, knowing that there's a certain gradient or magnetic field gradient, and knowing somehow the resonant frequencies of molecules in different magnetic fields, somehow it could reconstruct it based on that. That's about all I can say.
Actually, what the somehow is all about. Okay. Okay. So, if you remember, when we go back and had a pulse sequence here, when we give the 90 and 180 degree pulses, we put a gradient in this particular, let's say it's an axial slice, just to be specific, though that you could do this in any direction you want. It's an axial slice, and at the time of the 90 and 180 degree pulses, we'll put a gradient on where the top of the head is at a higher magnetic field than the feet. And it's a linear difference. So we go from high in this head down to low in the feet. Then if we send in an RF pulse of a very narrow frequency band, we will only resonate the nuclei that'll be in an axial slice through the body. And the location of that axial slice will depend upon the center frequency of the RF we put in and the exact frequency along the gradient. Does everybody remember that? That was slice encoding, right?
That's the Z direction now we're talking about.
Well, if it's an axial slice, that would be the Z direction. Sheila, you look like you're in pain.
I'm trying to remember all of it. Yeah, it's coming.
It's coming. Okay. Now then, so that would give us one direction. Now, once we start resonating the spins in one plane, we now need to determine the position of the signal in that plane, which is that. So that's 2 dimensions more that we have to worry about. So one of them will be at the time we receive the signal back over here after we've given the 90 degree pulse, after we've given the 180 degree pulse, and we'll wait another time period tau, we'll get a signal back. This will be at TE, right? Then we'll get a signal back. When we receive that signal, we'll put a magnetic field gradient. Let's just say it's right to left this time. That means the signal that we get back, if the right is low field and the left is high field, the signal that we get back from the right side of the body will be resonating at a lower frequency than the signal we get back from the left side. Therefore, all the low frequency energy will be from the right side of the body. All the high frequency
Hello?
energy will be from the left side of the body. How you doing, Yuri? Okay? So now we've been able to position the spins in the z-axis and now in the right-left axis, okay? All right? So here's just an example. If we have something on the, let's say the right side of the body, it'll resonate at a low frequency. Spins coming from midline or the left side of the body will resonate at a higher frequency. So the signal in the two voxels will resonate at different frequencies. When you add them up, you'll get a complex signal. And when we actually receive the signal coming back from the tissues, we'll get a very complex signal. This is a very simple one because it's only two frequencies. Well, we'll come back, we'll be in a range of frequencies all the way across the bandwidth that we're selecting to do the study.
And bandwidth is the selection, kind of the range of frequencies you kind of, not arbitrarily, but you kind of manually select and decide I want to sample this frequency to that frequency.
Exactly. And so you'll do that with the RF pulse. That's a narrow band, remember, because we're only the narrower the band, the thinner the slice. Remember that? And then what we're talking about here now is then when you receive the signal, you'll also only receive the signal through a band of frequencies, because any signal outside of that is just going to be noise. So you want to restrict receiving anything outside your bandwidth. So the bandwidth will be so that it will be selected so that the spins on the far right of the body you'll pick up, and the spins on the far left of the body you'll pick up. Any other signals outside of that you don't want to pick up because it's just noise. So what we'll then do is if we have, say, a 30 centimeter field of view, then we'll separate we'll put in a gradient on the field, and let's say we want a bandwidth of, let's say, 15 kilohertz. Then what we'll have, we'll select a gradient in that direction so that a negative 7.5 kilohertz will be all the way on the right side, plus 7.5 kilohertz above the center frequency will be signals on the right side, and we'll receive a signal bandwidth that will be 15 kilohertz in width would be our bandwidth. So we receive all the signals from all the way through. Okay, and then the center of that will depend upon the center frequency of the magnetic field. If it's 1.5 Tesla, the center of that bandwidth will be somewhere around 64 megahertz. Okay? So if we have two beakers of water, like we talked about before, if we have no gradient on, they'll all be at the same magnetic field. We'll get one nice, simple little signal coming back, and we'll get one peak. If, however, we put a gradient, a frequency encoded gradient on at the time we have these two beakers of water, there'll be a little bit of signal that'll be here at low magnetic field, a lot of signal at high magnetic field. We'll get a very complex signal coming back. And then if we do a Fourier transform to find out how much energy we have at different frequencies, you'll see that we'll have a little bit of energy that's a frequency corresponding to the small beaker, and a lot of energy from at the location corresponding to the big beaker. That all makes sense? Okay.
I guess we'll get to it, but we've still only accounted for two planes at this stage. We figured out what slice we're at, and we figured out where we are right to left, right?
Yes. The third one is much more complicated. These are the simple ones. We'll get to the more complicated one hopefully today. Okay? So it's important that you understand the first two, because the third one is much more difficult. Okay, so if there are any questions about the first two, you need to bring them out. And this is all very important. You need to know this stuff on a daily basis when you do your protocoling and determine these things. Okay, so that comes to chemical shift artifact type 1. Let me see. Who do we now have on? So we have, okay. So, Michael, are you with us?
I am. Can you hear me?
Yep, great. So what's type 1 chemical shift artifact?
Chemical shift artifact. It's where you have two different tissues in the same, two different tissues in close proximity to each other that have very different magnetic shields, or magnetic shielding, electron clouds.
Yeah. Okay, so if you have water and if you have fat, again, this is review from last time. The fat has these huge electron clouds. They shield the protons in the center of the molecule so that they are at a lower magnetic field than than protons out freely in space. Water has very few shielding electrons, so its protons basically see the full magnetic field. So that means, Yuri, if we have water and fat in the same voxel and we do an image, will the water molecules, will the hydrogen and the water molecules be resonating at a higher or a lower frequency than the protons in the middle of the fat molecules?
I believe they'll be resonating at the higher frequency compared to fat.
Great, good. Just so that you don't get confused, however, in the infinite wisdoms of physicists, when you look at a spectrum, they put the high frequency at the left and the low frequency at the right. So I don't know why, but well, actually I do, but that's a historical reason. But that's right. So the water will resonate at a high frequency. In fact, if we do a spectrum of protons within the human body, based upon what we've just talked about, the highest resonant is going to be water because it's basically in a molecule that has no significant shielding electrons, just a few. All the big macromolecules will have more shielding electrons so that their nuclei will resonate at lower frequency. So all of the information that we see in a spectrum is just going to be on one side of the water signal. So but we'll get back to spectroscopy later. So getting back to type 1 shift, magnetic shift. So if we're in a situation where we have a gradient and we have a voxel that has both fat and water within that voxel, and if we put on a magnetic field gradient and the computer thinks that we are doing frequency encoding, it turns out that both fat and the water are going to be in the same voxel. But as Yuri just told us, the water is going to resonate at a higher frequency than the fat, or a better way to put it is that the fat resonates at a lower frequency than the water, and therefore the computer is going to think that the fat is actually at a different position than the water. Because remember, the computer thinks that the position in the frequency encoded direction is strictly given by the resonant frequency. So if fat is resonating at a lower frequency than water, the computer thinks it shifted more, in our example, more toward the right side of the body. So what will happen, even though the fat and water are in the same voxel, when you go through, you get a signal, you're going to get signal from two different frequencies. When you do the Fourier transform, it's going to think that the fat is at a lower frequency than the water, and therefore it's going to separate their signals. This is type 1 chemical shift artifact. So they're basically in exactly the same location in the body, but the computer is going to think they're in two different locations. So it's going to, when it displays them on the computer string in the image, the fat's going to be shifted to the low frequency side. Okay? So, Sean, here's an example, a sagittal T1 weighted image through the ankle. What is the direction? What is the frequency encoded direction?
Let's see, the frequency encoded should be superior to inferior
How do you know that?
because the the tibial plateau is darker and the fauna is wider on the
Okay.
talus,
So
the
what we
talar
see,
dome.
great. So what we see here is that we've got what looks like a big black signal of the tibial plafond, but we see no subchondral bone on the talar dome. But on the bottom of the talar dome, we have this big thick black line, and then the posterior facet of the calcaneus, we see no subchondral bone there. And the reason for that is that the fat, the low frequency side of the frequency encoded direction is up, the high frequency is down, and all the fat throughout the entire image is shift upward. The water stays where it's supposed to be, so the articular cartilage, since it's primarily water, stays in the same location. The fat shifted upward, so we end up with a void here because the fat has shifted away. And we ended up with no void here because the fat is actually shifted up, so it's covering over part of the water. And we see the same thing here. And we see the same thing down here at the bottom of the cortex as well. Okay? So Sheila, what direction here is the slice encoded direction?
And it would be the slice encoding. Right to left.
Excellent. Good. So the slice encoding is through the plane, so it would be right to left. So that means that the last encoded direction, which is the phase encoded direction, is anterior to posterior. And this just is shows separation, overlap.
Do any other than fat, other than fat with its large like shielding effect, is there any other like substance that we deal with in the human body that have this effect, or is this really chemical shift as a fat artifact? You're only going to get it.
No, fat's just a very good example. And most of the artifact we see is just going to be fat and water. Other things shift, but they're not as extreme as fat and water. So we don't really see them very much on the images. But if you do spectroscopy and we start looking at the different chemical elements within the tissues, they're all separated at different amounts, and we'll get to that later. But they're usually not intense enough to actually produce significant signal on the image. Well, we'll talk about that when we get to spectroscopy. Okay, so let's
Dr.
go.
Cruz.
Yes.
Dr. Cruz.
Yes.
Yeah. So the water's not shifting, or is the water shifting just a little bit?
The water is shifting an extremely small amount.
Okay.
It's
Right.
better. It's best just to think of water being
Same.
essentially protons and out in a vacuum without much shift. But in actuality, it shifts an imperceptible amount.
Okay.
Because the oxygen and the H2O molecule does have a few shielding electrons. But that they're only a few as opposed to the thousands in a fat molecule. Okay, now let me just go over this one more time. And this is a diagram that was made up by Ray Kuo when he was a fellow here for an article we published in JMRI. So if you have a beaker of water next to a beaker of fat, and we do an image, and we use a bandwidth of 32 kilohertz here across the image. What you see when we do, if the frequency encoded direction is right to left, even though the two beakers of water don't overlap, the fat is going to be shifted to the left here, and so it's going to look like the two are going to overlap. Now, if we use a bandwidth of 32 kilohertz, and let's say we're using a 256 by 256 matrix, or 256 matrix in the frequency encoded direction, that means that if we divide 32 kilohertz by 256, that means each pixel will have a width of 125 hertz. So again, we've got 32 kilohertz, which is a typical receiver bandwidth, spread across the entire image. And these are big beakers of water and fat. But the number of pixels we have in the frequency encoded direction is 256. And then whenever we receive the signal, if we have signal within 1 pixel, we put it together to make an intensity for that voxel. So what it means then is we take 32 kilohertz of frequency, and we're going to divide it into 256 different intervals. And all the energy that we get in each of those intervals, we're going to assign it a number that would be the number for that pixel. So that means each pixel is 125 hertz across. Is that clear? Clear as mud, right? Now, if we go to 3T, that's at 1.5T. If we go to 3T, what happens is you have twice as much overlap, because at 3T, the chemical shift goes as the strength of the magnetic field, so you're going to get twice as big a shift. Actually, because of the nature of water and the nature of fat, the chemical shift at 1.5T is 220 hertz. That's what it is all the time, wherever you are, based upon the nature of the fat in the human body and water. If we go to 3T, that then becomes 440 hertz. Now, if we do the same image where we do a 32 kilohertz bandwidth and we have a 256 matrix, then that means, again, that each pixel is 125 hertz. But now, up here, the 220 hertz of the overlap, the chemical shift overlap, came out to be 1.8 pixels. Now, if everything else is exactly the same, then what you have, now you have a double the chemical shift. The bandwidth per pixel is the same. So instead of being 1.8 pixels, now the chemical shift is 3.5 pixels. And that's why if everything is the same and you go from 1.5T to 3T, the chemical shift looks like it's doubled. Here's just an example. This is the same subject. Here the patient was on a 1.5 scanner. We scanned the knee. Patient got off that, got on a 3 scanner, had everything else the same, and scanned it on a 3 Tesla scanner. Notice the chemical shift width here is twice as strong at 3T. Is everybody okay? Keep hearing funny noises. Okay. What?
That's not your phone?
No. Anyway. So everything else the same. If you double the field strength, you're going to double the chemical shift artifact. And therefore, chemical shift artifact can be much worse at higher fields than at lower fields. But now, if we come down here and we change things, if instead of using a 32 kilohertz bandwidth, we increase it to 64, we double the bandwidth. Then if you divide 64 kilohertz by 256, you'll end up with 250 hertz per pixel. And that means that since the chemical shift at 3T is 440, then if you do the math here, you come back to 1.8 pixels. The bottom line here is that if you double the bandwidth at 3T, then you'll come back and you'll have the same chemical shift that you had at 1.5T. So one of the way a lot of people get away from minimize chemical shift when they go to 3T is that they double the bandwidth. And here's an example. Here's the patient at 1.5T, same patient at 3T with everything being the same. We then rescan the patient at 3T by doubling the bandwidth, and notice the chemical shift is about the same as it was back at 1.5. There's a phase artifact here, which was a problem in the early days of 3T that has since been corrected. Okay?
What are you compromising by increasing bandwidth? Signal?
Michael, what are we compromising when we increase bandwidth?
I believe scan time.
No,
Scan time.
scan time's the same.
Scan time is the same?
Okay, now, if you remember what I said a little bit ago, is if we have bandwidth, at that time I was saying, let's say it's 15 kilohertz, I said you want to arrange the bandwidth so that you get the signal from the left side of the body and you get the signal from the right side of the body. But you
I think it's going to be increased noise then.
Okay. You don't want to get any signal outside that range because it's only going to be noise. The bottom line is, as you increase the bandwidth, you're going to bring more noise into it because there's a background of noise spectrum that's across the entire spectrum. So if you double the bandwidth, you're actually going to bring in a lot more noise. And the bottom line is that you will decrease the signal to noise by a factor of the square root of 2. Why it's a square root of 2 we could go into, or there's an article in Radiology that Bill Bradley and I wrote a long time ago that I could dig up somewhere where we actually explain why it's a square root of 2. Okay, so that's bandwidth. So you prefer not to increase bandwidth. Basically, if you go from 1.5T to 3T, you kind of double the signal to noise. But if you have to increase the bandwidth to get there, to get rid of artifact, then you increase the signal to noise by 2, but you decrease it by a factor of the square root of 2 because you've increased the bandwidth. So that means instead of getting a double of the signal to noise, your signal to noise only will improve by a factor of about 1.414, which is the square root of 2. So unless you do other things, if you just change the bandwidth, you're actually going to you're not going to be able to take to be able to use the full signal to noise that you should be able to gain by going to higher fields. So there are other ways to handle chemical shift that we'll talk about later. But you can also get chemical shift artifact in the through plane direction. That's in plane direction. Here, if you look at this is an MR scan of the brain. And if you notice here that there is this high signal intensity rim that's actually going through the periphery of the brain. Yuri, do you know what this is caused by?
Um, I don't. If I had to guess, it would be chemical shift.
That's a good guess. Not only can you get chemical shift in the direction of the frequency encoded direction, but you can also get it in the direction of the slice encoded direction. Again, remember with slice encoding, you put in a very narrow band of frequencies to only select the nuclei that are in the plane that you want to image. And then we do frequency and phase encoded to then further separate the signal within that slice. But just like before, if you put in a narrow frequency band, the fat is going to be resonating at a different frequency than the water, so that the fat slice you select is going to be at a different location than the water slice you select. And what happened here is the fat slice, the lower frequency direction is toward the top of the head. So this band here is actually the fat within the marrow space, which is basically a slice above the water signal, which is in the brain here. And it superimposes the fat within the marrow space onto the brain here because of the chemical shift artifact in the Z direction. And you can correct it here.
The fat signal just barely like cheating onto the anterior cortex?
Yes, this basically is the fat within the marrow space, essentially at the axial image that's one slice higher.
But it's just that little bit that's projecting over the marrow. Anterior,
Right in
further
here and
anteriorly
here.
is just the normal fat
Right,
enclosed space.
right. And if you correct for it, this is what it should look like. So you can also get chemical shift artifact if you're not careful in the Z plane as well. Okay. So is everyone reasonably comfortable now with slice localization and frequency encoding? Is that right?
Yes.
Sheila? Okay, Sheila's trying. Okay, let's go to the hard one now, which is the phase encoded direction. Okay, let's go back to the basics 2D spin echo pulse sequence. What we have is a 90-degree pulse and a 180-degree pulse. Those happen when we put on the slice encoded gradient so that we only resonate nuclei within the slice of the body that we want to see. Then we wait till 2 tau until we get the spin echo coming back. And when we get that echo, we then receive the echo, but when we receive it, we put on a gradient in the frequency encoded direction, or often called the readout direction. And that gives us another direction, which we talked about before would be right to left. We still have the third direction. which would be anterior posterior in this hypothetical example that we're talking about. That occurs from something that's called a phase encoded gradient, because we can use slice encoding and we can use frequency encoding only one time. If you do it twice, what you'll do is just get an angled plane. So we have to do something besides slice and frequency encoding to get that third axis. And with Fourier transform imaging, we use phase encoding. And it turns out, in order to do a 256 by 256 matrix, you have to do 256 different phase encodings that have to be all unique. And you can only do one phase encoding per sequence. Therefore, Yuri, how many sequences would we have to do? What would be the minimum number of sequences in this scheme for us to be able to generate a 256 by 256 image?
I think at least two.
No, you would have to do one for every phase encoding. We have to do at least 256 phase encodings. So that means you'd have to do a minimum of 256 different acquisitions.
Okay.
Okay. The time between each Sean, what's the time between each acquisition?
Between each acquisition, that would be the time of repetition or TR.
Yeah, that's okay. So the time between each each of these acquisitions is called TR, the repetition time. So Sheila, if I had a TR of 1,000 seconds, then how many seconds would I have to would it require from me to generate an image this way? How did you get 4 seconds?
Oh, I was thinking dividing 1,000 over 256.
You have to do 256 phase encodings, and you have to wait 1,000 seconds between each one. So it would be 256 times 1,000, or 256,000 seconds, right? Which is a while. You know, you can calculate it out. It probably comes to 6 or 7 minutes, something like that. Uh, so typically, if you did the standard, and this is the kind of imaging that we had to do in the late 80s and early 90s, each sequence took a long time. If you had a TR of 2000 and you wanted a 192 matrix, then it would typically take about 17 or 18 minutes to do each scan. And that was in the spine, and in the brain, we typically did 18-minute scans back until the early 90s when we came up with more efficient pulse sequences. Okay, so now let's talk about what this phase encoding does. For an example, let's just take a square beaker of water, and we're going to image that water. So let's just say that the slice encoded gradient is up and down. The frequency encoded gradient is right to left, and the phase encoded gradient is in and out. Okay? So we know how to get the slice encoding. We know how to get the frequency encoding. So we want to talk just about this third dimension, which would be in this thing in the y prime direction. So that would be depth along this way. So let me take that image, rotate it around, and let's just look at it here. So as all we're looking at is a profile through one slice here along the y prime direction, the phase encoded direction. And we would do one of these for every pixel in the frequency encoded direction. So if we're doing a 256 by 256 matrix, then to generate an image, we would generate 256 of these projections that are in the y prime plane in order to be able to fill up the entire three-dimensional space. So let's just look then in the phase encoded direction. What the signal should look like if it's just a beaker of water. You should have no signal outside the beaker at all. It should be black. At the edges of the beaker, the signal will go from 0 all the way up to a bright signal, and then when you get to the other edge, it's fall back down again. This is what's called a square wave. So again, the signal outside the beaker should be 0 because there's no water outside of it. Inside the beaker, we should have a nice uniform high signal intensity all the way through the water. Okay, and this is then what it should plot like if we were using mathematical formula. It should be a nice square wave. Now, the way, let's see, Aram, what is Fourier transform? What is a Fourier transform?
As best as I know, it's some kind of mathematical tool that helps you break down like the different frequencies in a complex, waveform.
What Fourier's theorem from, I believe, is the early 1800s, what his theorem said is that any well-behaved mathematical function can be exactly reproduced by a series of sine and cosine functions, by just adding them up in a series. And by well-behaved, what you have to have is if you have something like a function like we're seeing here on the left, it can't come back. You can only have one value for the function for each position along the x-axis, and you can't have any sharp turns here. So the beaker that we're talking about here is actually not a well-behaved function, but that's important. We'll see why. That'll help us understand what's going on in a little bit. But basically what we have, the function that we want to reproduce is this square wave on the left side. Now, if we do sine and cosine waves, if we take the first term of the function that we're going to show in a minute is going to give us this, you'll find that the first term is going to be just a sine wave like this. And this kind of looks like that, but it has not very sharp margins. So this would be the first order approximation using sine and cosine waves to come up with a function that's a real function that tells us what the signal intensity should be across the beaker of water. And this is kind of what it looks like. You'll see that this is very blurry, and you'll see later what this is an image of, but this is actually one that only uses the first 2 or 3 terms in the Fourier series, and it's just all a big blur, which is what you would expect if this is all we're getting that's supposed to be approximating the square wave on the right. Now the second term in this particular function would be 1/3 sine of 3x, which looks like this. It's not as tall as the first term. It's only 1/3 the size, and it has a higher frequency, which we see here. This doesn't look anything like the square wave at the left, but if we add this to the first term, this is what it looks like. So this would be sine x plus 1/3 sine 3x, and this looks closer to the function on the left than the original one looked like, right? Looks closer than this one did. Okay, and if we take a few more series here, this would be 5 frequency encodings, and we're seeing that it looks like maybe there's a little structure here that wasn't there before. And if we take more and more terms in this Fourier transform, the more terms we have, the closer it should be to the actual function we want to produce. This is if we go out to 15 terms, and this is what it would look like if we go out to 128 terms. And you can see this looks much more like that square wave than what we had before. Notice that this doesn't drop down as abruptly as what we would like here. And notice that you got all these wiggles here, and these wiggles will be important in a minute if you do this. And you could go out to 256 if you want. So, but this would be the first 128 components in the phase encoded direction, and it would give us a signal profile that's pretty close to what we wanted in the real image. And that just shows these are one phase encoded. This is actually phase encoded 2 directions here. This would be 5 phase encodings. If we go out to 128 phase encodings, this is what it looks like. So this was actually a coronal stir image through the wrist using the MagnaView scanner that not too many are familiar with right now. This scanner actually does what's called 3D Fourier transform imaging, where we actually do phase encoding in 2 directions. You have to because it's a non-uniform scanner. But this is what it looks like. As you go out to have more and more terms in the Fourier transform, you can find that the image quality, you get much more sharper margins, and it looks much more like the image that we want to see from inside the body. So that's basically what Fourier transforms do. Uh, if you take any mathematical function by using Fourier's theorem, you can calculate the series of sine and cosine waves that would be necessary to duplicate it, if you want to duplicate it as a sum of sine and cosine waves. It turns out that for the square wave that we're talking about, a beaker of water, what it would come out would be sine x plus 1/3 sine 3x plus 1/5 sine 5x plus 1/7 sine 7x out infinitely far. That would be the Fourier's theorem. That would be the sum of sine and cosine waves that would give you the square wave that we talked about before. And we saw how as we add those together, they become more closer and closer to duplicating the signal intensity function that we wanted to duplicate. Now, sine x, sine 3x, sine whatever x, those are all functions that we all know about, sine and cosine functions. What's important to determine from imaging in order to be able to do this is what the coefficients are in front. So what we just talked about, the first term, which would just be a constant, was 0. The coefficient that goes on sine x was 1. The coefficient that went on sine 2x was 0. The coefficient that went on sine 3x was 1/3. The coefficient that went on sine 4x was 0, out to infinity. So what you have to do is be able to find out what the coefficients are in front of each of the sine terms, sine and cosine terms. Okay? Now, and that's what we do when we do Fourier transform imaging, is that we put in pulses which will allow us to then determine what the coefficients are that go in front of the sine and cosine terms. And the way this works is, if we typically, if we do like a 256 encoding in the, let's just say it's the y direction that we're going to do the phase encoding in, we'll generally start out with a very strong positive gradient in that direction. And if it's 256, what we'll do is step that gradient down by interval steps. The first time it'll be a full strength, then it'll be the full strength decreased a little bit. And then you'll keep doing that until you get halfway through, in which case you'll have no gradient at all. And then as you keep going, you'll start putting negative gradients and you'll step through negative gradients is typically the way they do it. And so you'll end up with 256 independent gradients. The 0 gradient one, the signal that comes back, gives you the signal intensity of any term that goes at the front, a constant term that's not associated with the sine or cosine wave. In our example before, that was 0. So here's just an example. This is an old sagittal T1 weighted image through the cervical spine from about 1990. This is a 120. The phase encoded direction is right to left. Frequency is up and down, which you can tell by the thicknesses here of the cortex. And of course, the Z direction is right to left. What we have here in the 128 term, notice that it looks like you have a little black line going down through the center of the cord. And that was first concerned that could be the central canal of the cord, but it turns out that's just an artifact if you don't have enough phase encodings. You go to 296, we can see that we have a nicer image, a little bit sharper image of the chord. And if you go up to 256 phase encodings, we even get a sharper image, and we can see the details of the chord structure better at the 256 image. Now, so let me just reiterate. So when we do phase encoding, if we do standard old-fashioned spin echo imaging, and let's say we want a 256 by 256 matrix, then we'll have to do 256 different acquisitions, changing the gradient each time we do it. And the signal that we get back from each of those is going to be proportional to the the number that has to go in front of whatever the sine wave is that would be associated with that gradient. So if it's a very steep gradient, that would be a high frequency sine wave. Not a very strong gradient would be a low frequency sine wave. No gradient would be the constant term that goes in the front. And therefore, we can then, from the signal intensity that comes back, we can calculate the coefficient that has to go in front of the sine waves, which the computer needs in order to be able to generate an image. Now we'll come back to this, and I'll say it again in a minute. Okay, but let's notice here that we have these wiggles adjacent to sharp margins. Now these wiggles are caused by two different things, but they're often confused into one in radiology. They're often called truncation artifacts. See, I don't know who's next. Michael, what is the term truncation artifact? Have you heard the term truncation artifact? Michael, are you still with us? Michael?
Sorry, I'm here. I didn't unmute my mic here. I thought that truncation artifact was the same as Gibbs. Oh, the same as Gibbs artifact.
Well, then what is that?
Well,
They're not the same, but let's just say they were. What is that? What is it?
I can't explain it.
Okay, that's fine. If you notice that the more terms we used in the Fourier transform, the closer it looked like the square wave that a beaker of water should have. And let's just go back for a minute. When we truncated it, when we didn't use very many coefficients, we got a lot of big wiggles, and they had kind of a low frequency to them. As we had more and more terms, we got smaller wiggles at a higher frequencies. So what these wiggles would look like on an image would be bands at the edges of tissue interfaces. I'll show an example in a minute. So what we're seeing in front of us here are wiggles that are due to one is due to truncation artifact. The truncation would be this, in order mathematically for this to be an exact duplication of the square wave, we have to have an infinite sum we have to have an infinite series. That would mean take an infinite time to scan someone, which isn't acceptable. So if we stop at 128 or 256 phase encodings, rather than going to infinity, that's called truncation of the sequence, and that will give artifacts. Here, they're small artifacts if we do a lot of phase encodings. If we do less in phase encodings, we get much bigger artifacts. But that's a truncation artifact. Now, a Gibbs artifact is actually something, it looks kind of the same, but it's technically different. And that is that the Fourier's theorem states that you have to have a well-behaved mathematical function. If you have a square wave like we talked about with very sharp margins with an abrupt change, that mathematically is not a well-behaved function. because the first derivative of that function is infinite, because you have a very sharp, abrupt change. In the artifacts you get in Fourier transforms, when you try to do Fourier transform with a not well-behaved mathematical function, are artifacts that are called Gibbs artifacts. So, they're very similar in a lot of ways. They look the same on images, but they actually come from two different mathematical problems. Okay. So what do these look like? Well, here's just an example in the brain. Here you can see these wavy lines here in the brain, and this just looks like those little ripples that we saw at the edge, and these come from the two sources. One would be that we have Gibbs artifact because this is an abrupt transition, and the other would be truncation artifact, which is because instead of using an infinite series, we stop the series at 196 in this particular example. So those are the artifacts that you get at edges due to the Fourier transform technique. So let me just skip through this. Okay, Yuri, have you heard of a term called K-space?
I have heard of it. Um, I, I've heard of it. I'm having a tough time remembering what it is.
Okay,
It's the way we recreate a picture uh, on the screen, um, and um, but
okay.
that
Well, one way to think about this is that there are two languages here. And as you know, you can say the exact same thing in Spanish as in English, but someone who doesn't know Spanish isn't going to understand it, and someone who doesn't know English isn't going to understand the English. Uh, I like to think of it in MR, there is machine language that the machine knows and speaks in, and there's image language that we know and we speak in. Image language are the images that you read on that come up on your computer screen. But the computer, the the machine doesn't create uh, directly an image. What it creates is a thing called K-space. And they're just an image are the signal intensity numbers in three-dimensional space, where bright signal is a high number and black is zero. K-space is also a series of numbers in three-dimensional space, but those numbers are not really associated with signal intensity. The K-space numbers are just the coefficients that go in front of the sine and cosine waves that exist for each voxel in space. Or not each voxel, well, the voxels are a 3D representation of signal intensity in space. K-space is a different language which says exactly the same thing, but it's numbers in three-dimensional space, but there's not a direct one-to-one correspondence between the K-space numbers and the signal intensity numbers. Let me put it another way. Okay, so the bottom line is that the computer will generate a three-dimensional array or matrix of numbers. Once you know these numbers, which are the coefficients in front of the sine and cosine waves, the computer can easily take those numbers, throw them in front of sine and cosines, and calculate the, the signal intensity anywhere in space. Because it can take those numbers and go from the K-space numbers to the signal intensity functions in space, and then create a three-dimensional map of signal intensities within the human body. And it's that three-dimensional map of signal intensities that we look at and call an image. So from the scanner's point of view, all that we have to do is fill up all the all the K-space numbers in order for the computer to be able to calculate the images that we look at. Now, the way it fills K-space is what we've been talking about. So let's just talk about 2 dimensions right now, just the K-space of a 2-dimensional image. What we have is a frequency direction and a phase direction. If we do a single 90-degree pulse with a single value of the phase encoded direction, then when we put on the frequency encoded direction, we will get 256 numbers in the frequency encoded direction, right? So what happens is, in the frequency encoded direction, we'll put that on at the time we receive the signal. Then we know the spins that are low frequency will be at a low frequency amount. Spins at a high frequency will be spinning rapidly. So the spins on the right side of the body will be spinning slowly. Those on the left side of the body will be spinning rapidly. We'll get this complex signal that comes back on our wire. We'll have all the signals together in them. And then in that information, by doing a Fourier transform of that, we'll get the signal intensity, we'll get the amount of energy that's
Patricia, that's Jenny from corporate office on 8801, 8801.
corresponds to different positions across the body. So basically, one acquisition, when we acquire the one echo, what we're getting is one line of K-space. All the numbers along one line of K-space. Now then, if we do another acquisition, we put in a different phase encoded gradient, then we will fill up another line of K-space. And using standard spin echo imaging, what we'll do is 256 of those acquisitions, and we'll completely fill up K-space then. Okay? And then with these numbers, the computer can take them and then calculate the image.
And 256 is the
That's
orientation of matrix we have in the phase encoding direction.
Yeah, in this case, the direction this way is frequency encoding, and the number this way is phase encoding. They don't have to be the same. Just out of simplicity, I'm just saying they're both the same. And then what it looks like, this is what K-space would look like. If you fill K-space, you'll find there's more, there are higher coefficients in the middle of K-space. That's low frequency information. And there are lower numbers, intensities in the periphery of K-space, and these would be the high frequency components out there. Now, so this would be K-space. These would be the numbers in K-space. If you do a Fourier transform of that, that will put you into image space, and this is what the image looks like that corresponds to this K-space information. If you're trained properly, you should be able to look at this and make the same diagnosis as looking at the one on the right. Any questions about that?
Hold on. If you're trained, you're telling me people could read K-space like an image?
If you were smart enough to, yes. I don't know of anyone who can. But this, from a mathematical standpoint, this information is identical to that information. And here's another K-space. That's what it looks like when you do the Fourier transform. And there's subtle differences here. Okay, so K-space is basically the machine's information, not just. Okay. Okay. All right. So why don't we stop here, and people can think about K-space, and then tomorrow we'll bring it back up again, and try to make people more comfortable with it. All right. Any last minute questions? Okay. Thanks.
Thank you. Thanks so much.
Thank